Okay, 3.2 is a Kepler law. Kepler law actually got 3 laws. We need to know what is that. But the formula only got 1. Okay, 1. Now we're going to see the first one. Okay, Kepler first law. Okay, Kepler first law, they're talking about all planets that will move in elliptical. Okay, they're not circle. There's an elliptical orbit with the sun at one focus. Okay, this one focus, they're talking about sun. Sun is a focus point. Okay, another name for the Kepler first law, you can say there's a law of the orbits. They're talking about orbits, circle, the orbital. Okay, elliptical with the sun is a one focus point. Okay, just talking about the planet, how to orbit. Okay, so from here, this one is from the textbook. Suppose you can produce one of the ellipse shape by this one technique, how to draw. So from here, you want to sketch the shape of the ellipse based on the concept due to the foci of the ellipse. Now you need to using one of the pencil, okay, using the 120 cm track, 2 time tap. So you draw one of the straight line. Okay, this one straight line we label as a major axis. Okay, then you draw one vertical, there's a minor. Okay, 2 thumb tap. One of the thumb tap you put in 1 point, then you label this one is F1. Okay, so another one, the distance is the same, you later F2. So both sides, they also got point. Okay, after that, using your track. Okay, after that, join with the end, the thumb tag here, both sides. Then tighten the track to the tip of the pencil. So your pencil from the track, you're going to turn. Turn, that means make it become tight at the tip of the pencil. Okay, after that, you start to draw. Because they already fixed the point, the track actually cannot move already. So you can start from the F1. You're going to start to draw, pull until maximum. Then you go to down and continue to pull. So later you can see here, draw one of the ellipse shape. Okay, so it's one of the diagram to show you a video to show you how to draw. So you see, okay, they start. Okay, we got thumb tag, is it? So they start from here, bottom. Okay, pull until maximum. Then the line, you also pull maximum. So you find it. You draw one is an ellipse shape. Okay, so they want you to repeat the step 3 below and above. After you draw above, then you draw the below. After that, you draw the ellipse shape. Then you remove the thumb tag. Okay, remove the thumb tag. After that, you draw one circle. Draw one circle here. This one is represented by the sun. There's a F1. Okay, draw another circle. This one, same like the planet. The planet example is the Earth. Earth go to orbit the sun. Okay, so this was a technique, how to draw the ellipse shapes. Okay, now we're going to discuss. Okay, name the shape of the orbits used by the planet in the solar system. Actually, there is an ellipse shape. They're not circle. Okay, we want to use it as a circle because we're easy for calculation. Okay, suppose the shape is an ellipse. Okay, then we go and see the number 2. Describe how the distance between the Earth and the sun changes when the Earth make a complete orbit around the sun. So the Earth will move, continuous to move from the major, go to minor, after that and come back. So from here, they ask you, how about the distance? So distance, we find it, minor should be shorter. The minor distance should be shorter. Then how about longest? Longer is a major. Major axis is the longest. So from here, they find it, the distance is further at the major axis. Okay, when they just go to orbit, they find it, the furthest is the major axis. So from here, discuss how the shape of the Earth orbit would be the major axis almost as long as the minor. So they ask you, assume. Okay, we assume major axis and the minor axis is almost the same. So actually what we assume? We assume the Earth is a circle, it's a round. So that's why we take major axis as long as the minor axis. Suppose major is a longer. So that's why they got ellipse shape. Okay, but from here, when we do the calculation, we just assume both is the same. So we take it the orbit shape is a round shape. Okay, so if not the same, so you do the calculation very hard. We don't know the satellite is a major or minor, so the radius is a different radius. Okay, so from here, better we take it as a round. So major and minor is almost the same number. Okay, now we're going to see what the Kepler first law talking about. The planet in the solar system have the elliptical shape orbit. So important, they want to mention the shape is an ellipse. Okay, number 2, the sun is always stay at the focus of ellipse. That means the sun is never move one. They're only at the focus point of the ellipse. Okay, then the major sure longer than the minor. Okay, then we continue. Most orbit of the planet in the solar system have major axis and minor axis almost the same length. So from here, although there's an ellipse, but say most of the planet, we take it the round circle. Major and also minor, we take it as the same length. Okay, for the solar system lah. So from here, the planet can be assumed to make a circular motion around the sun. Okay, we take it is the same length, so we can say there's a make circular motion. Okay, and the last one, the radius of the orbits. Okay, the radius of the orbits, there's an average value of the distance between the planet and the sun. So we can say every part, the radius should be the same lah. Because you assume there's a one circular, so the radius orbit, there's an average value, the distance between the planet and the sun. Sure got bigger and shorter because the minor and major is a different. But from here, they just take the average. So the average, so all the planet, the radius should be the same lah. Okay, for every part also is the same. So this one is a Kepler first law. So they're just talking about law of orbits. Okay, how the planet go to orbit the sun. Okay, so now we're going to see this one. Minor is a vertical. Okay, this one short a bit. Okay, major should be longer. You see the horizontal quite longer. So if you find the planet when they move to nearest with the Earth, this part should be the nearest with the Earth. So we call it as a perihelion point. This point is a perihelion point. There's a place where the planet is closest to the sun. Okay, then when you find that until this part from the sun, they go to this part. And this part we call it there's a aphelion point. Aphelion point, there's a furthest to the sun. You are the very far one, far away from the sun. So these two is a different thing. So that's why they want to make it become easy for calculation for the radius. So they take average. So every part they plus together, divide. So everyone, the radius should be the same radius. Okay, so that one is a Kepler first law. No calculation, only the concept. Okay, Kepler's second law also is a concept. We're going to see the Kepler second law, what they're talking about. Okay, Kepler second law, there's a line that connected the planet to the sun. Okay, planet connect to the sun, swept out equal area in equal time. So that means this area that swept out, this one we call area, the time should be the same with another one. Okay, and also the area also should be the same with the another part for swept out. So this one's the second law they're talking about that. So they're talking law of the area. Okay, so this part, the planet go to sweep from A to B, one area. So another one, they go to C and D, also sweep out one of the area. So they find out A to B, the area, same like the C to D area. So this one from the Kepler second law. They're also talking about the time taken. Time taken to move A to B, C to D also is the same. Okay, so now we continue to see what's some more info from the Kepler second law. Okay, this one. If a planet that take the same amount of time to move from A to B, C to D. Okay, time taken is the same. Okay, area AFB. AFB, the triangle, is same as the triangle of the CFD. Okay, both areas should be the same. So that means Kepler second law only talking two things. One is a time, another one is an area. Okay, now we're going to see number 3. We're going to see the diagram AB and CD. When you see the diagram using the normal eye to see, A to B should be longer. The distance sure longer one, because from the diagram you can see already. C to D shorter. Okay, now we go and ask about the common sense. If I say the time taken is the same, A to B, the distance longer. So that means which one faster? Sure, A to B, you must run faster, because the time taken is a constant. Okay, I want 5 seconds. You need to start from the A, run until the B. This one also same. 5 seconds, you from the C run to the D. Sure, the A to B, you need to run faster one, because your distance is long. So I give you the time is a fixed time. So you run faster, achieve the B until 5 seconds. So C to D, you can run slow a bit, because the distance only short now. 5 seconds, you want to reach another destination, okay, you can run slowly. So that means distance is longer. Example for the AB, your speed should be higher. Okay, because you want to run fast. So from here, I'm going to show this means the planet moving linear speed A to B must bigger C to D. Okay, this one is not Kepler's second law. This one is what we understand. Okay, Kepler's second law only talking two things. Okay, so we continue to understanding the Kepler's second law. Okay, first one, time is the same, area is the same. Okay, this one from the Kepler's second law. After that, we go to conclude. Okay, we go to conclude is a distance. AB bigger than CD. Okay, how about the speed? Linear speed. A to B sure faster than C to D. So the bottom two, we go to analyzing. From what the Kepler law talking about. Okay, we plus about the distance, we plus for the linear speed. Okay, so this one is a Kepler second law. Okay, no more. So just like this only. Okay, the first one is talking about orbits. How to orbit the ellipse shape. After that, the sun is at the one focal point. The sun is never moved one, only the planet go to round the sun. Then they're talking about the major and minor. Okay, after that, they assume the whole orbit is a circular. Okay, that one is the first one. Second one, they're talking about the area swept out from the planet to sun should be the same. Okay, then they're talking about the time taken also is the same. But we go to analyzing the distance, sure got different. When the distance there's a further, sure the linear speed higher. Okay, because the time taken is a fixed. Okay, now we go to Kepler third law. Kepler third law, we got formula. Okay, the formula is related what we learned before. Okay, now we're going to see what is a Kepler third law. Okay, Kepler third law, the definition same like the formula. They say the square. Okay, the square of the orbital period. So that means the T, you go to square, go to cube, square first. Sorry, I go to square first. The square of the orbital period of any planet is directly proportional. So, directly proportional to the cube radius of the orbits. So, that means they're talking about the time taken and also the radius. Okay, time taken is a period square. After that, directly proportional with the cube of the radius of the orbits. So another name for the Kepler third law, there's a law of periods. So that means they want to count the orbit, the period is how long. Okay, different planet got different period for oscillating the sun. So from here, if you further, that means you find the time taken should be longer. So this one, Kepler third law, they want to mention about the time taken for the planet to orbit the sun is how long. Okay, so they create the formula is a t square directly proportional with the radius. Okay, then we continue. Okay, so this one is what the definition they want to mention. Okay, T is stand for orbital period. R is stand for radius of the orbits. Okay, if planet, okay, we never plus the H. Okay, remember? Okay, if this one I want Earth, okay, the Earth at the center. Okay, this one is the moon. Okay, this one we call it as a R, radius. Okay, radius from the center of the moon to the Earth. So this one we can say the R of the orbits. Okay, if the satellite are just you only add H. This one for the satellite. Okay, so if sun or moon this one that will straightforward give you what the R is total how many. Okay, you no need to plus the H. Okay, this one is a arrangement for the different planet go to orbit the sun. So the first one, nearest one is the Mercury lah. So you find it Mercury when they just round, there's a 0.2 years. Okay, one round. Okay, Venus is the second one, there's a 0.6 years. Okay, for the Earth, number 3, exactly 1 year. Okay, to round, finish one complete oscillation, there's a 1 year. Okay, after that, the Mars is 1.9, followed by Jupiter, then Saturn, then Uranus, and also Neptune. So the furthest one you find it, they take the longer time to be oscillate. Okay, so this one is relationship for the Kepler third law, period, and also the radius of the orbits. Okay, so we continue. Larger radius. So radius to orbit. The orbit, okay, example for the Saturn, orbit until here. This one called radius to orbits. Okay, so from here, radius orbits, larger, so the longer periods for the orbits. So further from the sun, longer the time to complete one orbit round the sun. Okay, time taken should be longer. Okay, so this one is orbital periods. So just now I mentioned already. So the Neptune is the furthest one. So they take around 164.8 years. Baru can complete one cycle. Okay, so this all is arrangement. So you make sure which one is the first, which one is the last. Jupiter is number 1. I need to know. So total we got 8 only. Okay, now we're going to see the formula for the Kepler third law, how to perform. Okay, how we going to create. Okay, Kepler third law can be formulated by the Newton universal law, what we learned before, and the concept of the circular motion. Motion is related with the centripetal force. Okay, now we're going to create. Planet make circle motion around the sun. Okay, the centripetal force is same as the gravitational force between the sun and also the planet. Means this one pull and this one pull must be the same. So that means the planet move, they will constant. They will constant to move. They never say, or some pull stronger than they near to the sun. Some the velocity very fast, then go faster. No. The pull things must be always the same. Just right angle only. Okay, just the angle is a tangent. So when they pull, the mass, the force is same value to pull to each other. Okay, so from here, this one is a centripetal force to pull. This one is the gravitational force. Sorry, centripetal force is pull here. It's the same thing, and this one only the velocity. Okay, velocity is moved there. So from here, we're going to see centripetal force to pull, also pull to the center of the Earth. Just the velocity want to move, then move to the another direction. Okay, wait. Remember, so just now we draw. I don't know if a mistake or not. Important, you remember we draw the tangent. This one. This one is stand for velocity. Not force. This one not force. If they ask you centripetal force, how to draw? Go to center one. Okay, gravitational force, how to draw? Go to center one. Okay, that's why they say centripetal force, same as the gravitational force. Okay, so remember when you draw the tangent, this one is the velocity. Yeah? Because just now you got one of the question I forget already. Is it call you to draw? That one when you draw 90, that one is a velocity only. Centripetal force memang is go to the center. Okay, only the velocity they want to show how to move. So there's a tangent with the circular. Okay, so centripetal force same like the gravitational force. So let you to know what's the symbol stand for what meaning first. Capital M, mass of the sun. Small m is a planet round the sun. Excuse me. Okay, the R. R is a radius from the center of the sun to the planet of the sun. Then F is a gravitational force. Okay, V, linear speed. That means when the planet, they got move, they got speed, is it? That's a linear speed. Then orbit periods. The planet, they want to orbit around the sun. Time taken is how long? Okay, so we got 6 physical quantity from here. Okay, so now we go to derive the relationship. Okay, remember the first one. Centripetal force. Gravitational force equal. So we put the formula lah. mv square over the r equal g capital M, small m. Small m is a planet. Capital M is a sun. So this one is a radius. So we put together. So finally, which one we can cancel each other? Planet, mass. We can cancel already. Okay, this one r square. When I cross over, multiply, this one r will go up. So one of the r will hilang. Okay, because it's square, this one r. So one of the r will be cut. So finally, I left how many? Okay, if I draw like this, if I do the calculation, r square, v square, I cross over, equal g capital M r. So this one r, this one cancel, become 1. So now v square equal g m over 1 of the r. Like this. So the calculation should be like this. So make sure you know. Okay, this one become equation 1. Okay, I take it as an equation 1. Okay, number 2. Remember we learned about this one. One circular. So now we're talking orbit is a circular, not ellipse. If ellipse, we need to do another formula already. So that take it as a circular. So circular circle, there's a 2 pi r. Parameter for circle 2 pi r. So from here, you want to get the v, velocity. Velocity is a displacement over time. So the displacement is how many for the one circle? 2 pi r. Okay, over the t. So now I want to take this whole thing, put in here. Okay, I do want v. I just want time taken, the period. So I put in, substitute 2 to 1. Okay, so v square will become 2 pi r over t square. Then GMR is the same, this one. Okay, now we can go and see which one we can cancel. Okay, actually nothing can cancel. The R also cannot cancel because the R, when you cross over, this one R square, is it? The R go up, become R cube already. So the square I put in 4 pi square. Then R cube. GM already go down. Then after that, the T square already. Okay, so I do the calculation here, let you to see clear. Okay, 2 pi r square over t square equal gm r. Okay, this one I cross over. Okay, go up. 4 pi square r cube already. Okay, over t square gm. Okay, now I want to move the t square, go another side. The gm come down. So the formula create. T square equal 4 pi square r cube over gm. So you find it. This one formula like almost the same what we learned before. Is it Tongzhen? Have you seen this one formula before?
Yes, teacher.
Suppose this one is a formula we used before. We go to find what? The mass of the sun, the mass of the earth. Remember? So the formula we learn is what? Okay, I write here. M equal 4 pi square r cubed over g t square. Suppose here. You want to find the t square? You move the t here lah. Then the m you come down. So suppose same like this formula. This one is a formula they just want to show you how to get it. Suppose we get it before already. Okay, when we want to find about the mass of the sun. Okay, so they just want to find periods. So you take out the t, go another side, then the m you come back. Okay, so now we're going to see continue the formula for Kepler. Still not yet come out. Okay, so now I get this one. Okay, why I put the bracket? I want to show you 4 pi square over gm. G and m is a constant value. What's a G? Gravitational constant. What's the m? Mass of the sun. Okay, we know already. That's a constant value. 4 pi square also constant value. So that means this whole thing actually is a constant value. Okay, what's the difference? Only the r and t different. Okay, when the planet circular, the time taken different, and also the radius sure different. The rest constant. So from here I can write gm is a constant value. Okay, from the Kepler third law. Okay, Kepler third law just now they mentioned this one. So if I ignore the directly proportional, then I put the k. K actually is what? If I plot the graph, t square versus r cube, directly proportional. So the gradient actually is a k. A gradient of the graph actually is a k. So k is a one constant value. Okay, so from here you focus this one. Just now I draw the constant value 4 pi square over gm. Same like the k. We compare this one and this one. You compare these two formula. T square, I also t square. R cube, I also R cube. Just the center is a constant value. So this one constant value represent k. K is a constant value. So I can say k actually is what? K is a 4 pi square over gm. Okay, one of the value is the same one. I don't care your planet at the first level, third level, final level, your k also same. Okay, because they count about 4 pi square is a constant value. G also same. Then the m for the sun, sure is the same. Okay, so this one k constant value. So in every planet, we also get the same number. So from here, I can create the formula already. Okay, we create the formula. Kepler third law, relationship between the t and also the r. Okay, we got two planets, planet 1, planet 2. So I just write the equation, compare the two planets. Planet 1, so I put T1. T1 square equal 4 pi square over gm bracket R1 cube. Okay, planet 2 also same. Only I put the 2. Okay, can you see these two also is a constant value? So I put k. Okay, both sides of k actually is the same value. So finally, I can create the formula. K constant value. Okay, so I create the formula. Okay, R1 I bring down. T1 square over R1 cube equal K. This one I also bring down. T2 over R2 cube equal K. So both sides also equal K. So finally I can put equal. This one equal than this one. Also equal K. So finally the formula from the Kepler third law, you can using first one, you can using second one. First one, if you're using T1, bottom sure R1. Okay? Another side, if you're using T1, Down is T2. This one, another side, sure, R1 over R2. So if you write T1 over T2, then later you R2 over R1, like this, wrong already. Cannot mix. 1 over 2 must 1 over 2. Okay, if you 1 over 1, must be T1 over R1. Then T2 over R2. Okay, so either one, which one you want to use, they can move one. Okay, so finally, this one is a Kepler third law formula. T1 squared over R1 cubed equal T2 squared over R2 cubed. So this one formula a little bit complicated when you press calculator. If only R, okay. If satellite R plus H, then you need to cube. This one is most complicated when you press the calculator. Okay, then the final answer, they say, I want to find period. I don't want T square. Then you need to square root some more. Okay, so we're going to see some example. Okay, so you're going to see the factor first. What is the factor to make it the periods and also the distance will affect each other? You're going to see first. Okay, orbiting the planet, the sun. What is the factor? Okay, now you see the first one. R is the distance between the center. Okay, between the center of the planet and the center of the sun. So if the R changes, that means you got changes for the periods already. Okay, this one's the first factor. Okay, second factor, satellite orbit the Earth. Okay, either the planet orbit sun, either the satellite orbit the Earth. Okay, so we need to count by using this formula. Okay, if the R satellite, distance between the center of the Earth and center of the satellite. So this one is a one I mentioned just now, complicated. Okay, is planet sun? Okay, no problem. Only the satellite with Earth, you need to plus one of the distance. Okay, this one's the second factor to do the calculation, how you find the periods. Okay, R is what? Radius of the Earth. This one radius of the Earth, normally they will provide 6.370 times 10 power 6. Okay, H is the height satellite from the Earth. Okay, so now you can see one of the question, they also inside the paper. You can try to do this one question. Better write in 4. Okay, you can see the diagram. Okay, diagram to show the radius of the Earth. This one is radius of the Earth to the sun. Okay, this is a Mars, another planet. They're also from the center of the planet go to the sun. So I can label this one R1. I can label this one R2 . Okay, up to you which one you want 1, which one you want 2. So if I take the Earth is a 1, so I need to know the time taken for the Earth is how many. Okay, if orbit period for the Earth is 1 year, so I know this one is my T1. Okay, how long does it take for the Mars to orbit the sun? T2. So that means I want to find the answer is T2. Okay, so I show in 4. Okay, R1 for the Earth. Okay, R2 for the Mars. Okay, R1 or T1 is a 1 year. T2, I don't know. So if you never convert the year become second, it's okay. Because final answer also in year. Okay, so from here we can start to do the calculation. Okay, the formula is a Kepler third law. Okay, then we just show this one is a formula. Okay, so T1, so you find the T1. T1 is 1 year. So R1 is the radius of the Earth. Remember, you need to cube. Then this one is a T2, I don't know. T2 is a period for the Mars. Then the R2 is the radius for the Mars. Okay, so from here you start to do your calculation for this question. Okay, later I'm going to ask the answer from Chen Yu. Chen Yu, are you here?
Yes.
Okay, you give me the answer.
Okay.
Okay, so from here they ask you the mass, is it? So from here you can think about the mass lah. Okay, there's a further, is it? Further, sure the time taken is longer than the Earth. Earth is 1 year, ma. This one sure is more than 1 year. So you do your calculation. If you get the answer is smaller than 1 year, that means you get wrong already. Okay, the time taken sure is longer.
1.87.
Okay, 1.87 years. Okay, so this one is a calculation. Okay, I put the T1. T1 is 1 years square. Then R1 cube. After that T2, I don't know. Then this one is R2. I go to cube. Okay, finally, I get the T2, this one. Then this one is a square one. I get 3.512 years. So I need to square root. Okay, 1.87 years. Okay, so we continue to the next question. Okay, next question, number 2. Okay, we see this one also same, but this one got satellite. Okay, now the diagram they show about satellite orbiting the Earth, with the H. Got distance, then after that in the period is 1.53. So I can take this one is a H, then after that this one is a T1, okay, for the satellite. Okay, what is the radius of the moon? Orbit, the period of the moon orbiting is 27 days. T2. Okay, moon orbit the Earth. Satellite also orbit the Earth. Okay, but the moon, given the radius of the Earth, this one. Okay, radius of the Earth, R. Okay, then this one H. But they never tell you the moon go to the Earth. The radius is how many? They never tell. So I don't know lah. So that means I just know T2 is 27 days for the moon to orbit the Earth. Okay. Then the satellite to orbit is 1.53 hours. Okay. After that, I need to find out what is the radius of the moon orbit. Okay. This one is what they want to find. Okay. So from here, you need to create the formula. It's the same Kepler third law. So I just show the info first lah. So this one is a T1. This one exactly I already plus. Suppose you need to do the first step. 27230 kilometer plus the radius first. Okay. So R2 I do know. That's one for the moon. Then the first one, the period for the Earth, I know 1.53. Then the T2 is 27 days. Okay, you can see 2 unit is a different. Okay, better we change to hours is more easier lah. Okay, day go to hour, you just multiply 24. Okay, then the H provided. Okay, now I show you. The first step you need to do this one. R plus H first. 6.37 power 6 plus 2.3 times 10 power 5. Okay, because this one is a kilometer. So after that, I get it, this one answer. Okay, after I plus lah, I get this one answer.